Today's presentation is about considering uncertainty in our personal decisions. I am Brian Putt, and I've been doing decision analysis for 25 years now. And I started doing decision analysis doing some of my own personal decisions. So let's start by talking about how we make life decisions. We make decisions as we grow up about what university to attend, whether it be the costs or the benefits, the pleasing the parents, risk of failure at that university. And then after we graduate, what company do we join? Do I go for the most money, location, where my friends are, significant other, and then should I buy a house, where, how much, all those kinds of issues. Eventually I change jobs, and how long do I stay with my current company? Oftentimes these days people only stay with the company 2 to 5 years. And then there's some safety questions that you probably make every day that you don't even think about, like using a handrails on the stairs or using the cell phone while driving. So these are some of the decisions we make. Some are big, some are small. But we need to have a process for making those decisions. How do you make your decisions? Should you make your life decisions differently than you're doing now? Let's think about a strategy table. I think this is one of the most useful tools in decision quality. And what we're going to do here is we need to identify what decisions are we trying to make in this particular situation. And here I've picked on an oil industry example because that's where that's my background. So there's questions here about the recovery method, water flood spacing, the number of rigs, which should be how fast I'm going to do something, and then the type of water flood pattern. And under each one of these decisions, there are different alternatives. So I'm not reading across this way. I'm going to pick one from each one of these columns. Sometimes one column may not be applicable. And those can become strategic alternatives. And if all combinations are possible, then I could actually evaluate with today's computers all the combinations. So let's come back to my personal decision of replacing the roof on the house. So my decisions I'm going to focus on are when to install the new roof and what type of roof to install. So as far as when, I could replace it now, I could replace it 2 years, or when it fails, whichever occurs first, or just wait till it fails, whether that be 2 years or 5 years or 10 years. And then the roof type could be shake, composition, or metal. And then I have a number of uncertainties over here. The cost to replace, when will the roof fail, inflation, investment return versus spending on the roof now. So if I don't spend the money on the roof now, what do I do with those dollars? Do I invest them in the stock market? Do I put them into bonds? Do I just leave them in the checking account? Another big one is if this roof fails in the middle of winter when it's raining, that's probably more likely than in the middle of summer, am I going to have to pay a premium, and how much, to have the roof fixed right then? Here's the results using my most deterministic values, my most deterministic input values. So I'm assuming it fails in month 9 and that the winter premium applies. And if I replace the roof now, it costs me $17,000. If I replace it in 2 years, if the roof lasts that long, it's $17,600. When it fails, it's $17,600. And cost to replace the roof if I wait for failure is $20,300. So on a net present value, the replacing now has no change, and these numbers go down. And so we can, by looking at these, it says replace the roof in 2 years or when it fails. So that's $16,000. What are the uncertainties to consider and their distributions? Now we're going to assume triangular distributions for all these uncertainties, and it'll be based on assessing a minimum value, a most likely value, and a maximum value. This does not have to be a symmetrical distribution. So for example, when the cost to replace the roof, I'm saying the minimum is $15,000, most likely is $17,000, and the max is $20,000. there's $3,000 difference here and only $2,000 difference here. And then in the winter, if there's a premium, it's somewhere between 10% and 20%. And when does the roof fail? Remembering I did this study some time ago. It would be September 2014, 16, or 24. And then I have some inflation uncertainties from 1.5% to 2.5%. And then investment returns from a negative 10 to a positive 10. Uncertainty is best understood with graphics. We can display uncertainty as a distribution function, cumulative distribution function. So this is the distribution function. It says over time, this is the frequency that it might happen. So clearly that's most likely to happen here in December 2016. Over here is the cumulative distribution function, which tells me what's the probability that it's going to fail by this date or earlier. So it's 30% chance it's going to fail. We can call that maybe August 2017. There's a 100% chance that it would fail by, it looks here like, sometime in 2024. So the question is, which do you like to think about and prefer to see? My preference is to see the cumulative distribution function here. Considering the uncertainties of the initial assessments on the cost of development, inflation, and investment return, we see these results. On a discounted basis, we see that the cost, we're trying to minimize this now, that replacing now is the best. And in nominal terms, it is also the best. What decision do we make? Did you answer now? And do you agree with the assumptions on inflation and investment return? If you don't agree on the inflation and investment return, then we need to start back, recycle, and do the analysis again. What if we could grow our investments more? What if inflation were higher? We can do sensitivity analysis on our study here. So let's test our assumptions. We can easily test different distributions of these ranges. We can also consider the correlation between inflation and our investment return. Let's test some different ranges. Inflation, 1.5 to 3, and investment return, minus 10 to positive 25. What do you think is the impact of these changes in assumptions? So here are my graphs, updated for the new assumptions. And now we can see that the red line, replace the roof in 2 years or when fails, starts to looks better than replacing the roof now. It's got some downside, and I call this the downside because remember we're trying to minimize. But you can see it's also got some upside here because it can be a lot less than replacing it now on a discounted basis. Even though on a nominal basis it is not. Why is that? Remember, we said previously that we had an investment return between minus 10% and positive 25. So when I can make a lot of money on my those dollars I would have otherwise spent on the roof, I'm actually better off. So once again, did you select replace in 2 years? Did you select now? The right answer may depend upon your personal risk tolerance. So if you're willing to go to Las Vegas a lot, maybe you're willing to take this green line here and wait till the roof fails. If you would never even think of going to Las Vegas, maybe you want to take the blue line because that's more there's more certainty in that blue line because it's more vertical. So what are the takeaways from this session? Considering uncertainty, no matter how bad, is better than not considering uncertainty at all. And then we can use graphics to better understand the range of outcomes and also to assist us in understanding the decisions we need to make. And then finally, uncertainty analysis can be used in both our everyday home decisions as well as in our work. So I hope you found this video valuable, and you can contact me at Brian Putt at theputts.com. Thank you. Bye.